So I'll be talking about IceCube today. Emphasis is going to be on computational and analysis challenges. And instead of the many LIGO talks, we have all of this crammed into a few minutes. So I'm going to try to give an overview of what we're doing and why, and touch on some of the approaches that we're using to solve them. So the key questions here in the science background here, we're trying to understand the sources of high energy cosmic rays. And this is the other non-photon messenger. So we're trying to understand what we have been missing all the time by looking at the universe in light, like the surprising abundance of intermediate mass black holes that LIGO has turned up. And also what happens to neutrinos when they travel cosmic distances. And the approach that we're using for this is to directly detect neutrinos that are emitted by these astrophysical sources. And you need a very large detector that's deep underground. So this is IceCube as a instrumented volume of about a cubic kilometer. This picture has the Eiffel Tower for scale. This is a bad scale. You really want more geological things, but I don't have an alternative picture handy. The footprint of the detector, for those of you on campus today, is just about exactly the same as the size of the UCLA campus. And the vertical height here is the height of the San Gabriel Mountains from sea level to the very top of Mount Baldy. This is a very large instrument. It was completed in 2010. It has 5,160 phototubes that are these individual little spheres here scattered through the detector. Each one of those is a glass pressure vessel about 30 centimeters across, containing a high-speed photodetector, primarily looking at the northern sky through the Earth, for reasons I'll talk about in a moment. And we're sensitive to all flavors of neutrinos of the three, electron, muon, and tau. Most of the astronomy that we're doing with this is using muon neutrinos for reasons that will also become clear in a moment. This is the picture of IceCube. This is the thing to keep in your head and try to remember the scale as we go through. This is an international collaboration. We have participants from all over the world in the light blue colored countries and many individual institutions. So this is what IceCube data looks like. This is a neutrino interaction. This is detector data happening in the bottom of the ice. So you can see this in this animation. Each one of these spheres corresponds to one phototube. The neutrino interacted down at the bottom. It was going up. You can see the nuclear debris shower when the neutrino interacted. I'll restart the animation. Down at the bottom, that initial thing, and then there's a muon that leaves and goes up and to the right, now to the center, with a lot of afterglows. This is what our raw data look like and what we're working with when we do analysis. This particular event, the issue is not so much finding it from signal to noise, relative to noise. The signal to noise on something happening here is into the 5 digits. And the issue is what happened and how. Another look at the data, a less animated perspective here, we collect these waveforms from each of the phototubes. You can see in the blue and the black colors here in the top right-hand plot, one of these individual traces showing the timing of 4 individual photons being detected at one of these sensors. And these are reconstructed into the photon arrival times in red. And you can piece that together in this picture in the bottom into the view of the detector from many different places. The timing and spatial distribution of all of these photon arrivals we put together to reconstruct the physics of what happened and to be able to do astronomy. One of the fun things that I'll come back to later is that these are being irregularly sampled in a quasi-hexagonal 3D grid, which makes some kinds of analysis tools very difficult to apply. It's a sample of what we're doing here. Most of our science is coming from astrophysical neutrino interactions that occur in the detector volume. Those come from all directions and reach very high energies, thousands of TeV, 100 times or so the energy of the Large Hadron Collider. We get nuisance detections, background from cosmic ray muons that are coming from above, of cosmic ray interactions in the atmosphere above the South Pole. The muon comes down into the detector. This is a picture of one of them, like a freight train, and lights up this giant detector and saturates large sections of it at very high energies. These are the same kinds of particles often as we're looking for neutrinos. A muon neutrino that interacts, like the one in the movie I showed a moment ago, makes a muon in the detector. These are also muons in the detector and have to be distinguished by other means than just the type of particle. from the neutrino interactions that we care about, and these are also billions of times more common. So most of the analysis effort in IceCube is removing events like this one on the right. There's a further nuisance from cosmic ray neutrinos. So these cosmic ray air showers that make the muons in this picture also make large quantities of neutrinos. They're genuine neutrino interactions, so cannot, under any circumstances, be removed by distinguishing whether there's a neutrino or not. But we need to discriminate against those to understand the astrophysical neutrinos that we're interested in. These cosmic ray neutrinos are not filtered out by the thousands of kilometers of rock underneath the detector like cosmic ray muons are. That's why we only see them coming down from the atmosphere. So they come from all directions, and they're still hundreds of times more common than the signal that we're interested in. One of the saving graces is that they're at lower energies, mostly below 100 TeV. So we have this window from about 100 to 1,000 TeV where we don't really have to worry too much about these atmospherically produced neutrinos. And our main task is getting rid of cosmic ray muons. To give a sense of the data rates here, IceCube detects 3,000 cosmic ray muons a second, more or less. Things like this picture I just showed. One neutrino, mostly atmospheric, locally produced every 5 minutes, and one individually identifiable astrophysical neutrino, some caveats there, every month. So there's a huge difference in rate between these astrophysical neutrinos and the cosmic ray muons, about 10 billion times. Our total raw data rate, which is overwhelmingly cosmic ray muons, is about 400 terabytes a year. So we're taking a fairly high data rate, not horribly high, but something that needs to be dealt with in a serious way. And the neutrino in a haystack title is that we're looking for that 1 part in 10 billion of these events that's interesting. So the key analysis problems here are that you want to identify the interesting events from that, identify that 1 in 10 billion. And we have this raw event stream that's almost entirely background cosmic rays. And then once you have those events, you want to reconstruct their properties. So the movie that I showed is an event that's not hard to identify necessarily, but still requires a lot of work, even though it has very high signal to noise. You want to know what the flavor of the neutrino is. There are 3 kinds: electron, muon, and tau neutrinos. You want to know where it came from, which tells you where the sources are, which we don't know. And you want to know its energy, which helps you discriminate against backgrounds, and then tells us also what kinds of energies the sources are making of neutrinos. One of the interesting things about this detector from a data analysis perspective is that the detector array itself is quite simple. So we have many identical photodetectors, there's 5,000 of them that are all more or less identical. And the hardware triggering, such as it is extremely simple. We don't have any control systems like in the last talk that need to be tuned. The instrument is mostly passive, and all we trigger on is whether there's any light in the detector. And you get light from Cherenkov emission from charged particles produced in neutrino interactions. And the result of that is that all of our science capability is coming from software and the data analysis portion of the instrument. So you can think about this in the same way that people build software-defined radios. IceCube is a software-defined telescope, first order, which gives us a lot of interesting possibilities here. And one of the other things I would mention is that overarching key analysis problem in IceCube is that the backgrounds from cosmic rays are so much larger than the signals from neutrinos that if you have some kind of selection as a false positive rate for detection of neutrinos, that needs to be absolutely tiny because we're starting with a signal to noise of something like 10 to the minus 10. And very, very rare processes in these background neutrinos in the background cosmic rays will swamp the signal that we're looking for. So these are the 2 questions we have here, and I've illustrated one of them on the left. The first neutrino that I showed you in the movie was a very clear event. This one is not so clear. It is a neutrino, and you can tell because of these 5 phototubes that have lit up towards the bottom of the picture in a row. This is a challenging identification problem to find this in place of various nuisance backgrounds. And then the other question here, graphical illustration of the previous slide. This is a very high signal to noise neutrino, where the neutrino traveled in from the right-hand side and then interacted inside the detector, deposited a lot of light, and then a charged muon produced in that interaction exited to the left. Time is running from red to green here. And here, there's no question that this is a neutrino because there's nothing else that could have brought energy in invisibly from the from the right-hand side. But we want to know what happened here, where this neutrino came from, and the details of the particle interaction. Putting those kinds of pieces of information together, let us measure the three main things we're interested in IceCube science. Anisotropy is where the neutrinos come from. That's the direction the neutrino was. The flavor, which tells you the dynamics of the sources, which we don't know, and that's distinguishing the three different types of neutrino when they interact. And then the energy spectrum, which also tells us about the dynamics of the sources. And putting those together, we hope to be able to put together a picture of what's happening in some very high energy, seemingly very distant objects that we understand very poorly at the moment. We have, as you can see in this bottom left-hand picture, we have neutrinos coming from more or less everywhere on the sky, and it is to an unusually isotropic degree that is hard to understand at present. So the way that these come together, if you detect where the sources are coming from, astrophysical point sources, you can understand by looking at those uh, how those are coming together. You can also use that information to do indirect detection of dark matter, use the energy spectrum to understand what's happening in these sources. And even if you can't identify them individually, you can understand their dynamics. You can also use it to probe neutrino propagation over long distances. We have very little information on what neutrinos do if they last for a long time, whether they interact with dark matter, for instance. And you can use the flavor to understand that one of these three types of neutrino, whether there's a non-standard interaction. You can also use it to understand the acceleration mechanism and use this magnetic field diagnostic around the sources. So the way we find these neutrinos, there are three main approaches that are used. The first is that you pick high energy particles that are coming up through the Earth. Cosmic rays go down. They're very well attenuated by thousands of kilometers of rock, so they don't come up. And neutrinos do go through the Earth. So we can use the Earth as a filter to find these uh, neutrinos by seeing particles coming up. This has this problem that you need to decide how well you really know the direction when you're worried about part per billion tails of probability distributions. You need to be extremely confident in your directional selection to be able to do this. The downside is also that you lose half the sky. Another approach that's used is that you can find, like the one that I showed earlier, where the neutrino interacted inside the detector. You can find particles where all the energy just appears out of nowhere inside the detector. Cosmic rays come from outside the detector. So by looking for things where energy deposition starts inside, neutrinos travel invisibly, you can select them effectively. The downside there is that you lose half the detector in the process because you have to use the outer boundary as a veto region to find things that are coming from outside. There's also a whole zoo of hard things that I won't go into in a lot of detail that you can try too. But the top two approaches here are the workhorses for IceCube. So one of the main tools that we use is trying to identify the topology of these events, and that tells you the flavor. So if you have a muon neutrino charged current interaction where a muon neutrino scatters off a nucleus and makes a muon, this is the thing on the left here. And these make long tracks. Muons live for a long time and deposit energy over a distance. And then basically everything else makes a big blob of energy. The shower of charged particles from the interaction is only a few meters long, and IceCube instrumentation is between 20 and 120 meters apart. So it looks like a big blob of light. And there's some asterisks down here of special case things. One of them is the first concrete analysis problem that I want to highlight here. A tau neutrino, when it interacts, does something more complicated. So it produces a particle that travels some distance, like the muon on the left here. But unlike the muon, it doesn't last for very long. So this muon here could have gone on for 10 kilometers well outside of the detector. And the tau goes tens to maybe 100 meters as it goes. So you'll see something that instead of looking like either of these, that looks kind of like a dumbbell. So here's an example of a simulated new tau interaction. We don't have any robust identification of these in data yet. And when they get to lower energies, the length of that dumbbell is proportional to the energy of the tau. And the kinds of energies where we're seeing astrophysical neutrinos around 100 TeV, that's only maybe 10 meters long. And you have to find that pattern of the production and the decay of the tau lepton that's made in the interaction in the data. So in this simulation, this is an attempt to do this using a convolutional neural network. And what's happened here is you've taken the individual PMT waveforms from the optical modules with the highest, that saw the largest amount of light, and plotted those as these lines. Those are displayed graphically as a heat map right above. You can see in the left-hand plot, there's two peaks where you see on the same optical module some light first from the production of the tau lepton, and then some from its decay a few tens of nanoseconds later on, which is the units on the x-axis. And then these show optical modules on 3 of these vertical strings deposited through the detector. And then we can use these images to train an image recognition neural network on simulation to identify these events and data. One of the challenges that we have using these kinds of image recognition approaches is that the detector is not a 2D grid of pixels, which most of these kinds of algorithms are built for. They may have colors, but otherwise they're designed mostly for camera images. And here we have this time domain 3D thing on this weirdly spaced grid. It reduces poorly. So we've come up with these kinds of summary statistics where you're looking at raw data and arranged in a way to make it look like a series of photographs. Now, this approach in this case seems to be extremely effective. This is something we have spent a lot of time trying to figure out how to do well. The other thing that we're trying to do with these events is to figure out where they come from. And the first order solution is really easy. So this is the same event that I showed earlier where there's a muon. It interacts in the red and then moves off to the left. The muon goes the same way that the neutrino did originally. So if you want to figure out where it came from, some level all you have to do is hold up a ruler to your screen and point backwards. And you can do a linear regression on these points, and you'll end up with something like half a degree angular resolution. If you want to do better than that, and you want to do better than that, there's a lot of things in a half degree by half degree box on the sky. A lot of things come into play. So I'll discuss some of those on the next slide. The other thing is that for these track events made by muons, this is very easy. The blobby events are very hard, and we struggle to get much better than 10 degrees there, which is enough for large scale anisotropy, but not really quite enough for doing astronomy. But it would be really, really good to be able to do this because with all of the events that we have and to the maximum accuracy we possibly can, is finding specific sources would provide a lot of insight into the acceleration mechanism. As we know from the LIGO detection, a multi-messenger thing where you actually have an electromagnetic counterpart, you gain a huge amount of information very quickly. And we would like to be able to have that. And our sensitivity is linear and angular resolution. It's a background dominated experiment at the moment. We have limited by source confusion. So we would like to have better angular resolution if we can, and that would improve our sensitivity dramatically. Doing this, there's basically two key problems. One is that there's quite a lot, it's an optical detector, and the ice that we have is extraordinarily clear for ice, but the mean free path for photons, the scattering length is still only about 10 meters, which is less than the spacing of our instrumentation. When you build these kinds of giant detectors, there's a trade-off between size and instrumentation density. You want density so you can have high quality information without worrying too much about the bulk properties of the material, like scattering by dust grains. But you can't build a very dense, very large detector without spending a hideous amount of money. So you trade off to get as sparse a detector as you think you can get away with to instrument the largest volume possible to get the largest number of neutrinos. And the trade-off for IceCube was here, where typically every photon is multiply scattered, but only a few times. So we have sort of order 2 or 3 scatters. And that's an interesting regime for a lot of reasons. It's not the diffusive regime where there are analytic solutions, and neither is it the direct propagation regime where you don't have to worry about these things. And instead, you have to try very hard to model this in quite a lot of detail. And the scattering, to make things more complicated, varies with basically everything. The pattern of scattering depends on the direction that you move in the ice. You have dust grains in the ice. You have problems with paleoclimatology. As snow is accumulated, the relative dust to snow ratio over the last 100,000 years has varied. And so parts of the detector have more dust than others. And the scattering is anisotropic because there's a quadrupolar deformation of the glacier as ice has come down from the mountains around IceCube and stretched it along one direction. And it's aligned the scattering grains of dust in that direction. So you have, and the degree of anisotropy depends on how far back into the past you want to go. So it depends where the light goes, depends in great detail on how deep you are in the ice, what direction you're facing, and the direction between the source of the light, the energy deposition by the neutrino, and one of the optical modules. The other problem is that, especially for muons, at these very high energies, they lose loss energy in a stochastic way. So we'll run into an atom and lose energy very suddenly and deposit a lot of light, and then go for a little while without depositing a lot of light, and then make more again in a burst, which makes them trickier to model than something that has there's a lot of degrees of freedom in modeling how they behave. You can see some of this here in this right-hand figure showing one event in data. The approach here, this is using a maximum likelihood method, is that you try to fit the spatial and timing distributions of the photon to some hypothesis, and then you maximize that likelihood until you have the best description of the event. So you can see here, this is an event view. These are little views of the waveforms on each of the optical modules where the lines are pointing. The crosses are the actual data. We have a model of the photon propagation. It's, as you can see, not always a great model, but a reasonably accurate one. And the blue line, that's the best fit. That describes the data reasonably well in most of these things. But it's been challenging to describe the ice in its full complexity, and that's limited our sensitivity. Uh, the difference between this shower event from probably an electron neutrino pointing forwards and backwards is the difference between the blue and the red line. So you can see the effect here, that you have a sharper features in the forward direction than in the reverse direction. If you have an optical module in front, it sees mostly direct light. If you're behind where the neutrino is going, the light goes forward and then has to scatter back, which smears out its distribution a little bit. So this is the game that we're playing to try to understand the direction of these kinds of events. These maximum likelihood algorithms are the things that we've used for most of our science results so far. We're recently trying to use machine learning methods to understand this better. And the main approach has been using especially convolutional neural networks trained on detector simulation and looking at one of a variety of observables, either raw waveforms or some kind of summary statistics about the waveforms, in order to try to incorporate some of these complications of how the detector behaves. These things are coming to the fore over the last couple of years. They've been limited to some degree by problems, again, with the highly irregular sensor geometry, and then a large search space. We need to have uh, very high precision in what we're doing. You want nanosecond timing resolution in a function. The optical properties of the ice varies everywhere through a cubic kilometer, and it is difficult to include all of that information. So I wanted to show what this actually looks like. This is a simulation of photon propagation done with a GPU-based photon tracking simulation that we use to simulate the detector. There's a neutrino interaction at the beginning of this video, and then each of these lines that's coming out are photons scattering in the ice. The white spheres are simulated IceCube optical modules. You can see this isotropization of the light as the thing turns into a ball. I'm going to restart this. There's initially a sort of conical shape. Now you can see a dipole, the light going forward and then backwards. But by the time it gets to the nearest optical modules, it's heavily isotropized and all of the photons have scattered multiple times. And what these expectations look like varies with the flavor of the neutrino, the direction the neutrino is going, the three-dimensional position of the optical module that you're looking at the thing with, and the three-dimensional position of where the light was emitted from. And this is also one of the prices you pay for having a natural detector like IceCube. We can't build a cubic kilometer volume deep underground, so we're using a natural glacier, but there's no spec sheet that comes with it, and the ice itself is quite inhomogeneous, and we have to model that and handle that in the simulation and also in these reconstruction of event properties. So some approaches that we're using right now, there's a table-based approach where we run basically this exact simulation that I showed in the movie a moment ago, and then try to tabulate what we're doing and then fit that with some kind of parameterizable surface. So we're using a 7-dimensional spline surface here that has 450,000 free parameters and is not sufficiently complex to describe the data. And that's had a lot of limitations. It making that surface more complex scales very poorly. The amount of computational time required to fit that 7-dimensional surface scales as the 14th power of the size of the input data set, which turns into a wall more or less immediately. Recently, there have been a bunch of interesting steps towards making a neural network based solution here, where you train this on the simulation to try to reproduce the waveforms in the individual DOMs. DOM is a digital optical module used by IceCube. So here we have this deep neural network that's been trained, and it generates reasonably accurate waveforms that you can see here as a function of moving an input neutrino interaction around. You can see this smooth evolution of the optical module waveforms, similar to what we see here. You would think forward and back, it changes the sharply peaked distribution into a later and more spread out distribution of photon arrivals. There's a recent paper on this, and that's something that I'm hopeful is going to do a better job than what we have. The extremely challenging modeling problem. So there's just so few symmetries to be exploited. Other things that we're trying to do is to measure the energy of these neutrinos. There are lots of choices to understand how you actually model this. You want to measure muon energy somewhere within the detector. Um, and the energy lost, you can see here, the energy loss on a log scale over distance for an actual track inside of IceCube is highly variable, and that needs to be captured somehow in what we're using to understand the actual energy of the muon. These events where you have this small blob of light, the shower is not so long or a little bit easier because you can just add up all the light that you see, and you get about 10% resolution that way. But there's this problem of moving back and forth between the simple case where you'd like to have an energy and this more complicated one where you have a muon that is not entirely contained in the detector and is bumping along as it goes and occasionally losing huge amounts of energy and then going dark for a little while and then losing huge amounts of energy again. And that's been a challenge to take this plot in the top left and turn it into a muon energy. So we're also actively investigating new approaches to understand this fairly simple one-dimensional data set, try to get a number out of it. Lower energy events also pose their own challenges. Here's a case where we've really aggressively been moving in the machine learning direction. So this is an event that has much lower signal to noise, still has some of these modeling problems with the ice despite the large statistical uncertainties. And this is a preliminary result from this summer using a convolutional neural network to estimate energy and direction and particle type from an event that looks like this, which is a lot harder to see what's going on by eye than some of the ones that I showed earlier. So computational framework that we're using for all of this is something called IceTray, an internal piece of software. It's a nice design, I think, that uses a sequence of processing that should read modules that are connected through a set of first in, first out queues. And the idea is that each one gets an event, piece of data called a frame, does some processing on it, may decorate it with more information, and then passes it to the next module and on and on and on. And by doing this one event at a time kind of processing, this keeps RAM usage down. And that's really critical for using the kinds of grid resources that we do. So we're using basically all of our computing on HTC style computing, especially the open science grid, with many serial jobs, each of them handing these single events down a processing chain and then coming back for another event. Because the events are independent statistically, this is an embarrassingly parallel problem so long as you can do one event at a time in this way, and we can just spin out more jobs to use more cores. We're right now beginning to hit some of the limits of this approach. Core counts on typical computing facilities are growing faster than the RAM in the nodes. The amount of RAM that we have per core for this model of submitting many, many, many serial jobs is dropping. And we are heading down fairly quickly towards the minimum amount of RAM required to describe a single IceCube event. And as we pass that mark, we're going to have to revisit this computing model. We're not quite there yet, but we will be there, I think, fairly soon if those kinds of trends keep going. One of the other challenges we have with IceCube is that we're operating at the South Pole, and there are many complications that come with that, but one of them is that we have very poor network connectivity. So we have about 100 gigabytes per day of satellite bandwidth and a 1 terabyte per day raw data rate. So we do a first pass at what these events look like using a few hundred CPU cluster that's at the South Pole that does online event selection, reconstruction, and real-time alerts. And we need to be able to fit whatever we're doing onto that kind of computing cluster. And that's also responsible for compressing our events. So we've developed an internal domain-specific compression algorithm called Super DST. DST stands for data summary tape, but actually it's super in that it's not just a summary, it contains the whole event. And the result is that it gives us this 10-to-1 compression that we need, that basically all of our events come by satellite, eventually, potentially with a 12-hour delay. The satellite's not in the sky continuously with almost no information loss. So we've put a lot of effort into these kinds of uh, custom algorithms to fit in the constraints of operating at the South Pole. I also wanted to give a few sort of technical notes. I've hinted at these things on machine learning that we're using. So we've used, I'm going to call classical machine learning for a lot of things for a long time, where we're using a summary of the data based on a handful of variables. The parameter space is constructed in a few dimensional space based on the results of maximum likelihood reconstructions and other kinds of summary statistics. This has been mostly used for classification of events. Um, it's been used for a few other things too, but nearly all IceCube analyses at some point have a classical machine learning algorithm of this type used in their event selection to remove cosmic ray backgrounds. And then recently we've been moving to extend the parameter space here closer to raw data, where we have something that looks like the PMT waveforms as the ultimate source of data. And this is useful. It can be used for classification, and it can be done early in the processing chain where event rate is still high, and we haven't rejected a large number of cosmic ray events because it often has a very fast inference time and is trainable to do more subtle things than we're able to do with other approaches. This is very new and not used so widely yet. So an example of these kinds of things is classification with these classical algorithms is used for background suppression of various events by finding things that look like cosmic rays and removing them, and some amounts of energy and uncertainty estimation, mostly by just piecing together various other reconstructions and trying to figure out how to weight averages of them to get the best energy estimation that we have. And then these deep learning algorithms, there's a really interesting challenges in developing them. Our actual raw data are extremely high dimensional. We have millions of data points per event, and we don't have the number of simulated events to fill that space effectively, especially given the large numbers of degrees of freedom and what we're trying to get out of that. Neutrinos can be very different depending on where they are in the detector. So we try to use some kind of data representation that reflects symmetries in the data, and those symmetries can be hard to find because I mentioned some of the problems with the ice and the detector structure that really complicates efforts to find good symmetries. The laws of physics are intrinsically symmetrical, and uh, the light originally deposited by a neutrino interaction, for instance, is rotationally and translationally symmetric. But once you put in the detector, some of that starts falling apart. So we've tried a couple of different approaches here with varying success. So some of them I mentioned, trying to understand identification of new taus, involve trying to reduce raw data to something that looks like a 2D picture. Other things that we've been investigating include trying to take the physics at the level where it does have nice symmetries and then use that as fodder for other reconstruction approaches where we can tell them more explicitly about the symmetry breakdowns that occur from the detector, which is the hybrid approaches mentioned in the bottom right-hand side here. I just wanted to wrap up with a few statements about what we're doing next and the next generation of these kinds of instruments. So we built IceCube, and there was no previous detection of neutrinos from an astrophysical source at high energies. We'd seen the sun with other instruments. And we have some new questions now that we have a very high signal to noise detection of astrophysical neutrinos and a few sources. So where there's a GZK neutrino flux that's produced by high energy cosmic rays interacting with the cosmic microwave background that we probably should have seen and have not. And that's a target for next generation instruments. We have this very bright, very isotropic background of high energy neutrinos that are coming from potentially high redshift objects. We don't know what makes it or how it's made. We have one confirmed source of neutrinos detected with IceCube, a source called TXS 0506 plus 056. But it's 4 billion light years away, which is unusual for an astrophysical object. Usually the brightest thing on the sky is not halfway across the universe. And then we have these interesting particle physics questions about what's happening to neutrinos as they travel that remain unanswered. We at least know they don't disappear because we're able to see an object 4 billion light years away. But beyond that, this could use more careful study. And then we're moving from the discovery regime to the precision regime, much like gravitational waves are right now, which is not the kinds of questions that we were asking when we built IceCube in the first place. So there's a different focus as we move to the next generation of things. So one of those three things that we're really trying to do, we're trying to get more events, which involves making a bigger detector. So you have some scaling that's something like square root of the number of events that you have. So this needs to become a lot bigger to really help with effective area, going from 1 cubic kilometer, which is too small, to something like 10 cubic kilometers. We want to really improve angular resolution. This is something where you get rapid improvements. The scaling and sensitivity is linear with angular resolution. We're currently at sort of quarter to a half degree levels, depending on the event. We'd like to get down to 0.1 degree or better, and that should improve the number of sources that we're seeing from 1-ish to 10-ish, which would be a huge amount of progress since we'd be able to see what these sources have in common. And then the other thing is we'd like to be able to do identification of flavor better. That's one thing that we have a really interesting source of information that you don't have in, say, gamma rays by looking at the difference between these three types of neutrino and how the ratio of those evolves with energy. And that relies on being able to find, like with this tau event, thing looked like a blob, like an electron neutrino. And if you look very, very carefully at it with the right tools, you can see that it's not. And expanding on those will be a major focus, and designing detectors that are able to do a better job of providing fodder for those algorithms is also a major focus of the next generation. So things that we're doing hardware end, very briefly, we have an upgrade of the detector that's a small infill array, these new red dots in the middle of the detector that are designed to provide very fine-grained calibration tools to better understand the optical model of the ice, which is our current limiting factor in sensitivity. This is funded and was supposed to be deployed starting next year. COVID has delayed that substantially, but hopefully it won't be too long. And then more in the future, not funded or even formally proposed, is building this much larger expansion to IceCube that would be order 10 cubic kilometers, much better angular resolution, new photodetector designs. But this is going to create lots of challenges moving forward. This is even sparser, and it's also going to become even more heterogeneous because we're going to have this large sparse detector and the dense detector in the inside, and it will be complicated to analyze these data. So some computational challenges that are coming up, we're going to have with this larger detector, it gets built a data rate that's increased by a factor of 5, not so forbidding, especially because we have a while to get there and computers keep getting faster. The thing that's going to be really challenging is that I mentioned there's this trade-off between instrument density, cost, and fine-grained information. The way that we build the large detector that's 10 times larger without spending 10 times as much money is we make it even sparser than the existing IceCube. So all of these challenges we have with reconstruction and selection are going to increase. And we'll have some slightly more granular data in some cases, multi-pixel photosensors, but we're still going to have longer baselines between detectors that are going to mean that we really need to do this optical modeling and inversion of the optical model with extreme precision to get the most science we can out of this larger detector. So we have, over the next decade, we stopped measuring zero, both with gravitational waves and with neutrinos. We have the first source of neutrinos. We know what we're targeting. We have this diffuse background that's been detected. We know what we're targeting, and we just need to measure it well now. And it will be an exciting period. So last slide for neutrinos, one neutrino talk for the meeting. I'll claim that this is the beginning of something really interesting, and we need to figure out how to exploit it well. And one of the neat things about IceCube, I mentioned it's a software-defined telescope to a large degree. So these intriguing new analysis approaches that we're starting to lean on hold a lot of promise to rapidly improve sensitivity even without a new instrument. If you look into this in detail, there are potentially factors of 5 or so in sensitivity to be gained with the instrument we have today with improved data analysis techniques. And that is the end of what I have to say.
Thank you very much.